Hey there, this is a video for my Intro Calc students. This is lesson 1.6, and we're going to talk today about limits as you approach infinity. And there's two very important ideas from grade 11 math that we have to make sure we understand. First, recall from grade 11 that if a geometric sequence converges, then it can be summed, even if the number of terms is infinite. Actually, especially if the number of terms is infinite. If you actually remember to grade 11, the formula for the sum of just n number of terms is of a geometric sequence is, let's see if I can remember this off the top of my head. Let's see, that's t sub 1 times 1 minus r to the n all over 1 minus r. That's the sum of, if you had, say, 12 terms of the sequence, 2, 4, 8, 16, 32, etc. If, however, you have a converging sequence, this one, of course, is not converging, it's diverging. But if you had a converging sequence, like, say, 1/2, 1/4, 1/8, 1/16, all the way to infinity, you could actually add up all of it to infinity using a much simpler formula. That's supposed to be an infinity symbol. Oh, sorry, I'm off the screen. The sum to infinity of t sub 1 over 1 minus r, which is, as you can see, a much simpler formula than this one. So see if you can recall those ideas from grade 11. Let's kind of put them in our notes a little more formally. Like I said, this is a converging sequence because the numbers here are getting closer and closer to some smaller value. They're actually, if you want, approaching 0. And remember that to get from this term to this term to this term, you're multiplying by r. In this case, r is 1/2. So the r for this sequence is 1/2. And you could sum this to infinity. You could say, all right, so the sum to infinity of this sequence is the first term over 1 minus r, which is 1 over 1 minus 1/2, which is 1 divided by 1/2, which is 2. And that seems very counterintuitive that you could add numbers forever and get 2. But remember, the numbers are getting smaller as you go. And forget this 1 for a second. Just think about the 1/2, 1/4, 1/8. Think about any finite distance. Like, say, the distance from this dot to this dot. From 0 to, I meant to go to 16, actually. I'm going to go to 16 here. That's an easier number to play with. So from this dot to this dot. There we go. So I could call this distance 1 unit. And obviously I can draw a line from here to here. It's not very hard. There, I just did it. But I could split this distance into 1/2, and then I could split that distance into 1/2, and I could split this distance into 1/2, and I could split this distance into 1/2, and I could split this distance into 1/2. And now I'm about to hit the limits of the width of my pencil, but let's suppose I could draw with an infinitely skinny pencil. There's really no limit to the number of times I could cut this distance and keep cutting it in half. I could keep cutting this in half infinitely. So if I add all of these little fractions together, there's infinitely many of them, but that doesn't change the fact that together they add up to 1 unit. This was a terrible problem philosophically for the ancient Greeks. It was known as Zeno's paradox. But modern mathematicians don't really have a problem with this. You can add together infinite fractions and get a whole amount, assuming that they're getting smaller by some rate. In this case, it was 1/2. And this actually really is this part of the problem. It's 1/2, here's the half part, plus 1/4, plus 1/8, plus 1/16, plus 1/32, and I could keep adding those forever, and I would get 1. So, of course, if you have an infinite sequence that's not converging, which would mean it's diverging, then what you would say about it is that there's really no way to sum it, right? If you add up numbers to infinity, you're just going to get infinity. And infinity is not really a number, it's an idea. So this doesn't have a meaningful sum, so can't be summed. Infinity is not really something we can work with mathematically. It's something we have to think about and work around. But certainly I can add this number of terms infinitely. This one I cannot. So that was one important idea. And basically, of course, maybe I should just back up for a sec. The r on this sequence is, of course, 2, because I'm timesing by 2 every time I go to the next term. So the conclusion that you made back in grade 11 is that an infinite sequence can be summed if its r value is less than 1. So if that makes sense to you, let's talk about something else from grade 11. Let's talk about the concept of the asymptote. Remember this graph, f of x equals 1 over x? It looks like this. Remember? It's two arms. Remember, when x is 1, and y would be 1, so 1, 1's a point. When x is negative 1, y would be negative 1, negative 1, 1's a point. But then as x gets bigger and bigger, you get fractions that are smaller and smaller. So as x heads to infinity, y heads to 0. If you'd like a better look at that graph, we could always go to Desmos here. And let me erase those guys. And there we go. There's the graph right there. And again, yeah, as you go further and further towards infinity, you get closer and closer to 0. Now, if I zoomed in, there would be some gap between here and here. And there's gap forever. I just have to increase the scale, or is it decrease the scale, at which I'm looking at the picture. So I'll never actually reach 0 for y, but I will approach it. So that kind of lends us to thinking that maybe we can do limits to infinity. As you head to infinity on some things, you'll actually get towards numbers. And they don't always have to be 0. For example, very similar to that, consider basically the same function but with a plus 3 on it. What does the plus 3 do it? Well, what does the plus 3 do to it? Sorry. Well, that's just going to shift the graph up 3, which means that instead of it now approaching 0, like it did a second ago, it's now approaching 3. Since 1 divided by x can't actually be 0, no matter how big an x I want to put in there, then this term can't be 0, so I can never actually get to the number 3 for the y value. So it will approach 3 as x approaches infinity. And again, I can show you that on the graph. You just shift that up 3, and that means that if I had the line y equals 3, as you can see, I get closer to it and closer to it and closer to it, but I'll never actually touch it. So you can say that I'm approaching it. Okay, so there's enough grade 11 review. Now let's put some of these ideas into practice with 4 very important examples for this part of the chapter. Example number 1, and I've decided to go back to the lined paper here so that I can better keep track of my writing. Example number 1 is find the limit as n approaches infinity of 1 over n. Okay, well, if you'd like, you could think of this as a sequence. You could think of it as, well, let's see. N could start out as being 1, in which case this would be 1 over 1. N could then be 2, which would be 1 over 2. N could be 3, it's 1 over 3. It's really like all of the possible fractions in the universe all getting together, and then this n is getting smaller and smaller and smaller. So think about what happens. As n approaches infinity, you basically get 1 over infinity. Now, this doesn't really mean anything. It just means I have 1 divided by a number that's getting so big that it doesn't really make any sense to even write it down as a number anymore in a conventional sense. And this is, of course, going to approach 0. Right? If I had 1 over a billion, that's a very tiny decimal. If I had a 1 over a trillion, that's an even tinier decimal. I'm heading towards 0. So I can say the limit as n approaches infinity of 1 over n is 0. And really, at the end of the day, 1 over n, 1 over x, call it what you like, it's still basically just this graph, isn't it? It's still that, and where you've shown that as x goes further and further on, y gets closer and closer to 0. So that's the first important example. Second important example is this guy. Think about what this would be doing. The limit as n approaches infinity of -1 to the n. Okay, so what can I say about that? Well, let's just count n in whole numbers. Anything to the power of 0 is 1, so when the first term, if n is 0, I get 1. What happens when, maybe we should make a chart of this. I never thought of this till now. Let's make a chart. X. Sorry, I forgot we used n. Suppose we had n and -1 to the n. Okay, so when n is 0, we get 1. When n is 1, we get -1. When n is 2, we get 1. When n is 3, we get -1. When n is 4, we get 1. We toggle back and forth between positive and negative. Okay, and that's just the integers, right? Think about it. If I were to put, say, 1/2 in here, well, that actually isn't even defined, right? Because you can't, remember, -1 to the 1/2 is like saying the square root of -1, and that's not a real number. But 1/3 is, because that'd be the cube root of -1, which is -1. So this thing is going to have a hard time even existing everywhere. Desmos can give you a shot at this. It'll try to graph. It'll make some sort of randomy dots in some places. But at the end of the day, it doesn't really know what to do about the fact that, you know, between 0 and 1, there's infinite fractions. And like we just showed, some of those fractions will be defined as answers and some won't. Some of them will be +1, some of them will be -1. How does Desmos toggle back and forth in an infinite scale between 1 and -1? It can't. So it kind of just does its best job and just kind of shows you some of the dots. You can, of course, actually ask Desmos to solve some stuff. Like, for example, I could say, well, oh, Desmos, if f of x is equal to -1 to the x, find me f of, here's one that we just did, find me f of 1/3, and it'll say, oh, no problem, that's -1. But again, if I put in 1/4, it'll say I can't 4 through to negative. So that's undefinable. So what does that mean for the limit? Well, think back to what we did in the previous part of the chapter, where we found out that if you can't approach a limit from both directions and get the same value, you can't say that it exists. So the limit as n approaches infinity of -1 to the n does not exist, because it toggles back and forth between two values and it's not approaching either of them. All right, so that was important example number 2. Important example number 3 is this guy. The limit as n approaches infinity of 1/2 to the power of n. Okay, what am I going to do with that guy? Well, for that guy, what you can think of is, you can think of 1 to any power as just being 1. So this is the limit as n approaches infinity of 1/2 to the n. And again, think of this, if you like, as a series. What happens when n is 0? Well, then I get 1/1. What happens when n is 1? I get 1/2. What happens when n is 2? I get 1/4. What happens when n is 3? I get 1/8, etc., 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 to infinity. And again, think about what's happening. This number is going to get infinitely big, so that's going to be 1/infinity, which is approaching 0. Okay? Again, I can kind of show you that on Desmos. If I wanted to graph, I called this one g of x, I am approaching 0 as I go infinite towards x is approaching infinity. Okay, so those are kind of just some almost like basic rules of how it works when you're working with infinity. Here is a new algebra technique, and this is what you're going to use for most of the stuff we're going to assign in the homework. The new algebra technique is basically this. So I would like the limit as n approaches infinity of n squared minus n over 2n squared plus 1. Okay, well, notice if I plug infinity in right now, I'd get infinity squared minus infinity, which is infinity, and I'd have 2 times infinity squared plus 1, which is infinity. I'd have basically infinity over infinity, which means nothing. That doesn't tell us anything about this graph. We're going to use a new algebra technique. We need to basically eliminate the fact that this is infinity over infinity. If we had 1 over infinity, hey, then we know we have a number that's heading towards 0. If we have infinity by itself in the numerator and some other number in the denominator, then we know that, well, it's heading towards infinity, no limit exists. But right now, infinity over infinity tells me nothing. So the algebra technique that we are going to use, and this is really clever, is we are going to, I'll write this in words, we divide the numerator and denominator by the highest power of n. So in this question, there is an n squared here and an n squared here. So we are going to basically take the limit as n approaches infinity of this thing like this. Now, if that's making you feel kind of weird about stuff, let me point out that, remember, this thing started like this, right? It was n squared minus n over 2n squared plus 1. And really, when I say I divide this numerator by n squared, that's really the same as just timesing it by 1 over n squared. Remember, dividing is the same as timesing by a reciprocal. And then if I did the same thing to the bottom, hopefully you don't feel weird about it when you think about it this way, because really I'm just timesing by 1. Right? Isn't that the same thing we do when we do common denominators? Isn't that the same thing that we do when we multiply by a conjugate? We multiply top and bottom by the same thing. It doesn't really change the value of the original expression. But when you multiply this out, you're going to get what we just got here. You're going to get the numerator over n squared, the denominator over n squared. And I'm going to distribute that divide. So it's the limit as n approaches infinity. And n squared divided by n squared is 1. N over n squared is 1 over n. 2n squared over n squared is 2. And then 1 over n squared is 1 over n squared. But now, when I put infinity into those things, think back to the example we did a couple of examples ago, we can consider 1 over infinity as 0. So this is like saying 1 minus 1 over infinity, all over 2 plus 1 over infinity. And yes, infinity and infinity squared are both infinity. So that is 1 minus 0 over 2 plus 0, which is 1/2. Considering we started with infinity over infinity, to find out that the actual limit is 1/2 is maybe a little striking. But once again, I can kind of demonstrate to you that that must be true. Oh, I didn't put this one in yet. Okay, so you get to watch me type it. So I have, I'll call this one h of x because I already have f and g on there. H of x is equal to, so the original function was x squared. Well, we were using n, but it doesn't really matter what letter you use. Minus x all over 2x squared plus 1. And if you take a look at that really odd looking function, you'll see that this line is getting bigger and bigger. It's 0.4 now. Let's move over a bit. And there it is. It's 0.45, 0.46, 0.47, 0.475. Keep going. 0.8, 0.48, 0.486. Guess where it's heading, folks? It's heading to 0.5, also known as 1/2. Will it ever get there? Nope. It's an asymptote, actually. But it is heading that way. I know what you're thinking. You might be thinking, what do you mean it's an asymptote? Back here, it actually crossed it. See, that's higher. Well, they didn't tell you this in grade 11, but actually, vertical asymptotes can never be crossed. Horizontal asymptotes actually can in parts of the function. But certainly, as I head towards infinity in the x direction, I am never going to cross. I'm going to approach 0.5. So 0.5, as we saw in the work, is my limit. Oops. Teams, go away. Is my limit. So there we go. That is 1.6's lesson. Example 4 is kind of the big one, the important one. most of the assignment questions you're going to do are going to involve you needing to use this algebra technique. So that's, as I like to say, another tool for your toolbox. All right, good luck with the assignment.